Welcome to the HBK webinar, Tips for Selecting a Power Analyzer for Electric Drive Testing. Now, all attendees' microphones are muted during the webinar, so please type any questions you may have into the WebEx Q&A dialog. You can open the Q&A window by selecting the Q&A icon in the WebEx toolbar at the top. Now, today's presentation will be emailed to all attendees. The webinar will also be posted on our website. If you have any additional questions, please contact our technical support team at support@usa.hbm.com. Well, it's time I introduce myself. I am your presenter for today's webinar. I am Mike Hoyer, Applications Engineer for HBM HBK. For over 30 years, I've enjoyed some exciting applications in electrical engineering, in data acquisition, and automotive, aerospace, power industries, providing solutions for customers worldwide. So it's been an exciting adventure and looking forward to many adventures yet to come. And actually, I started as an application engineer for Nicolay, that's an old name, for high accuracy and high speed data acquisition solutions back in 1991. And here I am 3 or 4 acquisitions later. Lost count a little bit. Actually, the last acquisition was more of a merger a couple of years ago between HBM and our sister company Brule & Care, or B&K, and I'll share with you more on that at the end of our presentation. Well, today's webinar is titled Tips for Selecting a Power Analyzer for Electric Drive Testing. Well, here's the agenda for today's webinar. We'll start with what is a power analyzer and what is electric drive testing, and then we'll get right into the tips for selecting the right power analyzer for electric drive testing. We'll talk about the importance of accuracy and measurement uncertainty. We'll talk about the number and type of inputs. We'll talk about the dynamic power measurements that are needed for electric drive testing. We'll touch on raw data storage and talk about some of the advanced analysis needed, and then real-time results and integrating your system, your power analyzer, into your automation system or control system. And then we'll wrap up with a conclusion, and be sure to stay tuned till the end where I can share a variety of links on where you can obtain additional information on many of today's topics. All right, let's begin with what is a power analyzer and what is electric drive testing. All right, so what is a power analyzer? Well, basically, in simple terms, it's a test instrument for measuring the power flow in electrical systems. It can be used for consumption, loss, measuring efficiency, could even be power generation. And it's used in many applications and in many industries, although there's no universal solution to every power measurement challenge. But more importantly is, why do we use power analyzers? Why do we measure power? Some things come to mind, I'm sure, like improving efficiency and performance. You want to be able to have that electric car go further and consume the least amount of power so it can go further, minimize loss. You want to reduce costs, avoid downtime. And you want to determine the origin and type of power issues sometimes in a system. Also, you want to ensure safety of products and operators and comply with standards. Now, to accomplish these tasks, you'll need to measure, analyze, and gather as much information as possible, and often at the highest accuracy, especially if you're wanting to improve efficiency. Okay, so what is electric drive testing? Well, here's a simple diagram outlining some of the elements of an electric drive system. Starting from the left, you have the power source. It's often a battery, or it could be a DC bus, sometimes AC. And then you have the power converter, often an inverter changing DC power to AC power. And then a motor using AC power to convert electrical energy to mechanical power. But what is the goal? You want to be able to maximize the efficiency across the entire drive system. And you can do that by maximizing torque per amp for as many points as possible by using clever battery techniques, inverter techniques, machine designs, and implementing appropriate control techniques. Again, to accomplish that task, you need to measure, analyze, and gather as much information as possible and at high accuracy, especially when you want to improve efficiency. Seems to be a trend here. All right, so let's start talking about selecting the right power analyzer for electric drive testing, starting with accuracy and measurement uncertainty. All right, so measurement accuracy is fundamental when you're optimizing the performance of an electric inverter, motor, or drivetrain. In fact, by decreasing measurement uncertainty, you can generate more credible results. In fact, best-in-class accuracy provides engineers with reliable data for understanding how to optimize inverter-driven machines. Now, selecting a power analyzer with the best base power accuracy available is an investment in the long-term future of your products and solutions. In fact, you also want to make sure you select a power analyzer with the best torque and speed accuracy, especially with the ability to use digital frequency signals for noise immunity, which means you'll need to identify the accuracy of the timer counter inputs on the power analyzer. And what good is the accuracy of your power analyzer if you haven't checked that you're using high accuracy sensors, including current sensors, since current is one of the more difficult signals to measure. Also, if you're using voltage dividers, you need to identify the accuracy of those sensors as well, torque transducers, speed sensors, and so on. So all that becomes just as important. Well, as it turns out, there's no standard definition for electric power measurement accuracy. In fact, every manufacturer defines their own method, and often you may see one banner spec, for example, 0.03% accuracy or measurement error, but then you need to ask yourself, 0.03% of what? Of voltage, current, power, DC only, or AC, and at what frequency? At what power factor? At what input range? Is it with or without averaging? With or without filtering? In fact, is the accuracy specification a pass-fail guaranteed spec? Or is it just a typical spec, which means it's not guaranteed? Well, these are questions you need to ask yourself when you're reading the data sheet, and you need to make sure you read all the fine print. So ideally, a power analyzer's accuracy specification should include accuracy along with quite a number of pieces of information, actually. In fact, here's a datasheet example of a 3-channel power card for a power analyzer. Now, first, we have the banner spec. It says 0.015% of reading, which is often listed as gain error, and 0.02% of range, often listed as offset error. And if you're looking to seriously improve efficiency, well, this is one of the best banner specs I've seen. Well, next, the accuracy specifications on the datasheet should be detailed and identify whether they are pass-fail, otherwise known as guaranteed specifications, or just typical, otherwise known as not guaranteed. Now, in this example, the datasheet specifies or states pass-fail limits, so they're guaranteed specifications. Now, also, it's good to have more detail, including formulas, tables, frequency plots like you see here, and specifications over a variety of power factors, frequencies, and input ranges. When it comes to measurement uncertainty, it would be ideal to have examples with formulas. Like you see here in this example, we see formulas and examples for 2 different power ranges for DC power and RMS power at 10 kilohertz and a power factor of 1. Well, now here's a portion of a data sheet, a small example on measurement uncertainty with tables, and again over a variety of voltage, current, and power ranges, and over a variety of frequencies from DC to 100 hertz, kilohertz, 10 kilohertz, 100 kilohertz, 200 kilohertz, and even 500 kilohertz for both reading and range specifications. It is also just as important to have detailed specifications on the accuracy and measurement uncertainty of your timer counter inputs and torque and speed measurements, again over a variety of frequencies, measurement times, or update rates like you see here in these examples of data sheets. Now, all accuracy specifications are needed on all inputs and all the sensors you'll be using to help identify the overall accuracy of the entire measurement chain. Well, our next topic when selecting the right power analyzer for electric drive testing is the number and type of inputs. Now, ideally, you'll want to select a power analyzer that meets your needs today and can easily be expanded for tomorrow's applications. Now, a modular approach means that your power analyzer can be easily expanded with more acquisition modules, offering more power channels and timer counter inputs for torque and speed measurements, making your system future-proof. So, for example, you may start out with a one inverter-driven application requiring at least 4 power channels plus 1 torque and 1 speed sensor input. So let's say you start out with a 7-slot mainframe. You need 2 3-channel power cards, which also include timer and counter inputs for torque and speed. Then maybe tomorrow you'll have a 4 inverter-driven wheel application, each having a 3-phase inverter. So you'll need at least 13 power channels plus 4 torque and 4 speed sensor inputs. So to expand, all you need to do is just add 3 more 3-channel power cards that include 4 timer counters for torque and speed inputs. So when buying a power analyzer, you'll like to make sure that your investment is future-proof. Well, it's time to identify the number of channels needed to record. We'll start with power. For example, this is a 3-power channel card with a high accuracy of 0.015% of reading plus 0.02% range. And for voltage, it can measure directly up to plus minus 1,500 volts DC. It has an auto range, which is nice to minimize measurement uncertainty, and it can sample on every channel up to 2 million samples per second with a bandwidth of 1 megahertz and 18 bits of resolution. If you need to measure a higher voltage, you can actually add in this differential probe with 0.1% accuracy up to 5,000 volts. And if you need to measure higher voltages, let's say up to 20,000 volts, there are options that also include isolation. Now, to measure current, ideally you'd want to use a high accuracy medium bandwidth zero flux current sensor. There's a variety of sensors with ranges anywhere from 50 to 2,000 amps, providing up to 1 megahertz bandwidth and accuracy 0.01%. up to, 5 kilohertz. That's a really nice high accuracy current sensor. And it's recommended for high accuracy. But there are other options for current probes, Rogowski coils. However, they're less accurate. And then you use those when bandwidth is more important than accuracy or you don't have enough room for a CT. Sample rate and bandwidth, well, let's take a look here. You got 2 million samples per second on every channel with a megahertz of bandwidth, as I mentioned previously, with 18 bits of resolution. But there are other options are available for higher sample rates, which are up to 250 million samples per second per channel, even with isolation. Well, there are additional channels that need to be recorded, and they're just as important. For example, torque and speed signals ideally should be recorded with timer and counter inputs. So you want to ideally record them digitally or use a frequency output so that you can gain the highest signal fidelity so that you have noise immunity from EMI. So if you have an example, a 4-wheel motor measurement, you'll need 8 timer counters, 4 for the torque, 4 for the speed. Here we have an example of a torque sensor. It's one of the highest in the world, 0.007% accuracy, and it has low latency speed measurement system. It's better for a DQ0 transformation, and it has a very high bandwidth, about 6 kilohertz, so you can do torque ripple measurements. And when you have higher accuracy, then you're going to have higher efficiency measurements for accuracy as well. Temperature measurements also become important, whether it be standard thermocouples, RTDs. Here's even a temperature module that's insulated up to 1,000 volts and can even handle up to 2,500 volt transients. Lots of isolation. and handles quite a wide variety of thermocouples. There's also vibration, microphone inputs. You want to do noise and vibration, NVH. A number of different modules can be plugged into your mainframe to make those measurements. Maybe you want to do strain measurements, multi-axis forces and moments. Here's a nice sensor that can do that, along with cards that can accept and provide the signal conditioning. Then there's also CAN and CAN-FD for bus data, a valuable input to be recording, so you can correlate the data from the CAN along with the measurements that you're making as well. And then for high voltage, low noise, and shielded cables become important. So having the appropriate cables with your power analyzer becomes important to shield signals for low noise and high safety. Here's a cable that is capable of measuring up to 1.5 kilovolts, and it's got CAT ratings available in CAT 3 for 1500 volts DC and 1000 volts CAT 4. Moving on to our next topic, it's dynamic power measurements, a very important factor when selecting the right power analyzer for electric drive testing. So a little bit of background on dynamic power measurements. First, a traditional power analyzer was originally created as a static power analyzer designed to measure steady state systems like an electric power grid, where the frequency really doesn't change all that much. It's around 60 hertz or 50 hertz. So therefore it uses an analog PLL phase-lock loop for cycle detection, and really only works when that frequency is steady state. There's no change in the load conditions. So measurements are not available when the frequency does change, like in a motor. So to test variable speed drives, you really do need a dynamic power analyzer. It needs to be designed to measure power during load steps, run-ups, and rundowns, ideally using digital cycle detection, which searches for zero crossing points on one of the fundamental phases of current, and the measurements therefore are available continuously, even during dynamic load changes. To calculate AC electric power accurately, you need to identify the cycles of the signals. Now, determining the time frame for a full cycle or even a half cycle can be difficult because the frequency and rotational machinery is often changing. So using a DSP, digital signal processor with advanced algorithms, one can filter one of the phases of current in real time to determine the cycle time by locating, for example, the zero crossing points as seen here in the diagram. Now, cycles can be detected in real time and even during load and frequency changes, and can be used to accurately calculate RMS voltage and RMS current, power, efficiency on each half cycle in real time, which can cut down on analysis time and offer results in real time as feedback to a control system. It's a really fast and accurate solution. Also providing a recording of the cycle time or cycle detect signal as seen in the diagram, looks like a square wave. It gives an added layer of transparency to the test by letting users know how the calculation was done. Here's an example of vehicle acceleration from 0 to full speed. Now the top signals include the 3 phases of current plus the cycle detect signal. In the middle are the 3 phases of voltage, and on the bottom are the values calculated for every half cycle for active power, reactive power, and apparent power. Now using cycle detect enables measurements to be calculated continuously even as the fundamental frequency is changing, which enables you to characterize real-world scenarios such as acceleration, deceleration, increase in load or decrease in load, going up a hill, down a hill, that kind of thing, and even develop efficiency maps significantly faster. More on that in just a moment. But first, I want to let you know that cycle detect also allows you to calculate electrical power and mechanical power over the same cycle accurately, therefore eliminating the greater than 1 efficiency results often mistakenly seen on traditional power analyzers due to the calculation of electrical power and mechanical power over different cycles, hence out of sync calculations. Having accelerated machine efficiency mapping is a significant advantage on a power analyzer because it can save hours of time and can be achieved with cycle detect. So, as mentioned previously, a traditional power analyzer needs quite some time to settle on a changing fundamental frequency to deliver stable results. And the typical time frame for one set point could be as much as one reading every 10 seconds, for example. Now, cycle detect can compute results every half cycle, easily completing a set point in less than a second. So in this example, we have 280 set points, which includes 20 different speed values as seen in area A, and 14 different torque values for each speed step as seen in area B. Now for each set point, a 1-second recording is performed, then a 100 millisecond pause to move to the next torque step and onto another measurement. After an entire torque ramp, there's a few seconds pause to proceed to the next speed step and then on to the next set of torque steps. So the entire efficiency map is done, in this example, in about 8 minutes, whereas the typical power analyzer would take at least 10 times longer due to the 10-second settling time between changing of frequencies, and there would even be some added wait time for the motor to cool down. Hence, this accelerated efficiency mapping saves expensive test lab time.
The acquisition has started.
Well, here's an example of an efficiency map with about 160 set points, and it's done in about 80 seconds. Now you can set up any type of an efficiency map and table. For example, you can create a map for inverter efficiency or motor efficiency or even efficiency of the entire drive line. Now you can set the efficiency table with any results you prefer and have them stored to a separate CSV file, comma separated value. Now in this example, we've got torque on the left, in the middle we've got speed, and on the right we've got efficiency in the table. However, you could add additional parameters to the table if you like, and in this particular example, we're just about halfway through here. We've got up to 109 now, 112. So you can see how fast efficiency mapping can be done when you do have cycle detect, because you don't have to wait for measurements to occur. The measurements are continuously being done because it's searching for the zero crossing points. Here we are at 152, almost up to 160. In 80 seconds,
the acquisition is complete.
Set points. That's pretty good, pretty fast. Well, now we're going to talk about raw data storage and analysis in order to select the right power analyzer for electric drive testing. Well, most power analyzers do not store raw signals, and ideally, a power analyzer should have the capability to store raw signals at a high rate, like 500 kilosamples per second, 1 megasample per second, even up to 2 megasamples per second per channel for extended periods of time. Having the recorded signals gives transparency to your measurements, and you don't just get a power value, you actually get all the data that went with it. In fact, storing raw data should be a prerequisite so you can easily and quickly audit your measurements, recalculate and validate your power results, or even do a deep dive into your control algorithms, and allow you to correlate tests to models at any time without having to run the entire test again, which can take up costly lab time and resources. It's also important to have public formulas. As you see here, you can actually see how the results were calculated. It's another way to audit your measurements. You should also have the ability to create your own custom formulas, ideally calculated in real time and for post-examination for advanced analysis. Well, here are some examples of the automatically created calculations made in a power analyzer using cycle detect. So as seen at the very top of the diagram, the cycle master out is the cycle detect signal, which is the result of locating the zero crossing points on the first phase of current. So all the remaining calculations for RMS current, RMS voltage, true power, mechanical power, all the way to efficiency are all referenced to the cycle-based signal, cycle master out, which means they're all calculated in sync or calculated on the same cycle. Well, the waveforms you see here are actually the calculated results you saw on the previous slide. This is actually a test I did on a small little dyno that had a bike brake on it, and I just pressed on the bike brake 4 times. The mechanical power P mech is on the top with torque M and speed N overlapped, and in the middle is the total apparent power S and the total active power P. Machine efficiency is in the lowest part of the picture here, and this example is over a 50-second time frame. Now, having these results displayed over time compared with the raw data enables further analysis of the inverter characteristics. A power analyzer should also offer a variety of ways to either select from pre-configured setups or even allow you to make a custom configuration and automatically create all the necessary power flow and power calculations based on your system's configuration. So in this example, you can choose between a basic mains or DC or machine to 3 or 6 phase machines, motor generator setups, DC or inverter powered E-axles, or even map your own custom configuration. Well, this becomes a very convenient way to view and understand large systems and saves lots of time not having to create all the power equations because they're automatically created for you based on the configuration. In this example, a drivetrain containing a battery, source, front and rear inverter plus a front and rear axle is mapped to display the power flow and the power measurements. This in turn simplifies the setup, display, and analysis. The power analyzer should provide the ability to create custom live efficiency mapping for the inverter, motor, and entire drivetrain in an effort to more easily optimize each part of the system and the drivetrain as a whole. Here's an analysis example of space vector or Clarke transformation. Space vectors are a mathematical way to simplify the system from a 3-phase system to 2 entities. So the 3 currents seen in the upper left are converted to I alpha and I beta seen in the lower left. One signal represents torque and the other represents magnetic flux. Displaying the 2 signals, I alpha and I beta, in an XY plot shows any unbalance and the control behavior. By applying the space vector transformation, it's a bit easier to understand what's going on in the machine. Here we're displaying the 2 entities, I alpha and I beta signals, as an XY plot. This shows any unbalance and the control behavior, in this case during an electric motor bike acceleration. This can be displayed live, or you can play back the analysis like I'm doing here after the test, since all the data was recorded. For DQ0 transformation, also known as Park transformation, you need the angle of the motor, called YMEC in this example, to transform the space vectors I alpha and I beta into a rotational coordinate system. So the resulting D and Q traces are directly a measure of torque and flux and are basically DC values with some ripple, so now the motor can be easily understood. Actually, inverters think in DQ0 entities, since this is what they compute. So basically, this allows you to compare the calculated DQ0 control measurements from the power analyzer, which can be streamed to your dyno and compared to your inverter's DQ0 control measurements. This helps engineers developing inverter firmware understand how well their inverter works with the motor, and maybe decide they need to change the firmware to achieve better results to improve the efficiency, especially during control changes. Now, a power analyzer should have a wide variety of advanced acquisition and advanced analysis applications, such as vibration analysis, CAN bus correlation, live DQ0 transformation, harmonic analysis, dynamic power capabilities, transient torque, torque ripple, live efficiency plots, and much more. In fact, these features are made possible by the storage of raw data plus real-time and post-analysis equations, which should be automatically created for you based on the configuration of your drivetrain setup. Well, it looks like we've worked our way down to our final tip here, the real-time results and integration for selecting the right power analyzer for electric drive testing. A standard readout after making power measurements may be sufficient for some users. However, engineers need more information, therefore need to visualize data, perform custom calculations, or generate results in real time, and often perform many numerous analysis functions, including efficiency maps and so on. Be sure to select a power analyzer with full data transfer to automation systems and refresh rates of up to 2,000 times per second. This means your dyno, otherwise known as your automation control system, will get results when you need them. Real-time feedback and communication with a control system makes test automation possible. You want to be sure your power analyzer has standardized buses and real-time equations, combined with a variety of control options to simplify the automation process. Now in this picture, in this example, we've got real-time feedback or results provided from the power analyzer in the test cell to the control system or the automation system via CAN 2.0 or CAN-FD, EtherCAT, or API, providing anywhere from 500 up to 2,000 blocks of information per second. Communication is done between the automation system and the power analyzer in the test cell through LabVIEW or .NET, C#, C++, Python, or even TTL signals. So you want to be sure your power analyzer offers a variety of communication methods and control options for seamless integration. Make sure the power analyzer solution offers a list of system integrators and their customers where the analyzer was successfully integrated into automation systems. Well, now we've come to the conclusion and where to get additional information. Well, just before we get to our conclusion, I just want to mention that all the fine specifications in this webinar were actually on HBM HBK products, from power analyzers to power cards, data sheets, torque sensors, CTs, multi-axis sensors, high voltage cables, temperature modules, and all the real-time and post-analysis functions. So just a quick summary on one slide. We'll mention the HBM Power Analyzer designed for electric drive testing offers a full range of future-proof configurable mainframes, anywhere from 2 to 17 slots for power analyzer cards, up to 51 power channels, up to 12 torque and 12 speed sensors, fiber optic remote control, and SSD for local raw data storage. And there's also the 3-channel power analyzer card. It offers power accuracies up to 0.015% reading and 0.02% of range, 3 voltage inputs, directly measuring up to plus minus 1500 volts DC, and 3 current inputs for CTs or clamps. Sample rates to 2 megasamples per second per channel at 18-bit resolution with an onboard DSP and user programmable math and digital cycle detection for reliable results. And then there's the high accuracy torque and current transducers, T12 HP with accuracy up to 0.007% with a speed option with reference pulse, and full range of CTs from 50 amps to 1200 amps. Actually, there's even one up to 2000 amps, and a slimline power supply. And then lots of accessories from EtherCAT, CAN-FD for real-time data transfer, CAN-FD for input for bus data or thermocouple modules, vibration and microphone inputs for NVH, and cards up to 250 million samples per second, high voltage probes up to 20 kV, and high voltage low noise cables. It's a complete power analyzer solution. It's time for our conclusion. It's time for a review on how to select a power analyzer for electric drive testing based on accuracy and measurement uncertainty. Well, we learned that the best accuracy offers reliable and credible data. And you need to review power analyzer and sensor data sheets in detail, especially you want to read the fine print. You also need to identify the number and type of inputs needed for your particular application, not only for today, but for future expansion, and a modular solution becomes very important. You want to be sure and review the inputs for voltage, current, torque, speed, temperature, CAN, NVH, and whatever else you may be recording. Dynamic power measurements is very important. The digital cycle detection enables measurements during dynamic load changes. In fact, it creates efficiency maps in a matter of minutes instead of hours. Raw data storage and analysis is very important. Storing that raw data saves costly lab time. You don't have to go back and do the test again. It offers quick validation and correlation with data in the past with the present. You can do advanced setup and analysis. That's going to enable you to understand how to improve your system. And then real-time results and integration. Real-time feedback and communication with a control PC or your automation PC makes test automation possible. And having a variety of communication methods and control options makes for a seamless integration with your automation system. Well, here's some additional information. In fact, here's a link for the HBK Electric Power Testing YouTube channel, which is growing by leaps and bounds. Lots of information available. Videos on just about every electric power testing topic you can imagine. Then there's also electric power testing knowledge base from white papers, custom application stories, videos, and tutorials available at the link shown here. And there's also electric drive testing solutions available at www.hbm.com/eDrive. And as I promised, who is HBK? Well, the quick answer is HBM is a leader for more than 70 years in test and measurement, fatigue, and reliability analysis, plus custom sensors, merged a couple of years ago with sister company Brewin Care, or B&K for short. Leader in sound, noise, and vibration and NVH engineering services for more than 75 years. Now combined as HBK, the leader in integrated solutions for any test from a single partner. So what does this mean for you? Well, instead of working with two companies, you get to work with one for almost any solution in the measurement chain, including HBM product solutions such as a wide variety of sensors for torque, force, strain gauges, and data acquisition systems, including high channel count, low and high speed, and rugged systems, plus power analyzers, which we've discussed throughout this webinar, as well as amplifiers for industrial control and analysis software for fatigue and durability and reliability. B&K product solutions include sound and vibration analyzers and analysis software, sound level meters, complete vibration test systems with shakers and controllers, and acoustic end-of-line test systems, plus microphones and accelerometers. So with the merger, HBK can now provide you with a complete portfolio of all these solutions, plus comprehensive engineering services in our lab or at your site, which means shorter development cycles, optimized products, and better decisions. All right, before we just wrap things up, I see we've got a couple of questions in our Q&A. Can data be easily saved and exported? Yeah, actually what happens is when a test is completed, it automatically saves the data to hard disk behind the scenes for you. And the data file actually contains all the setups and the entire environment of the test automatically into one file. However, you can certainly export any part of the data between cursors, one channel, all channels, the channels you're displaying, into just about any type of format you like, even to MATLAB or ASCII and you name it, UFF. So that can be easily done manually, or you can have that done automatically at the end of the test. You can have it automatically export for you any number of channels for the test. So that's no problem whatsoever. Okay, another question here. How is efficiency mapping actually automated and done quickly? Well, I'm assuming you're talking about with the automation system, because we already talked about how it's done quickly with cycle detect. And actually, I think I have a screen I can show you on how that is done with the automation system. So here's a screen I found for the internal process and data flow for efficiency mapping. So essentially you set up the power analyzer for the acquisition you're going to perform, the currents, the voltages, torque, speed, and what have you. And then you set up the efficiency map that you want to create, because it can be on just the inverter, the motor, or the entire drivetrain, and identify what items you want in your table. And then you set up the start of acquisition. Essentially, it will wait for a trigger, and that trigger can come from your automation system either via a digital I/O input, or it can be from a CAN input, or it can be from .NET or COM, from another third-party software that you may be using. No problem. Very easily done. When it does get that trigger command, it then performs the acquisition, which can be however long of an acquisition you decide it to be, and it logs the results that you've laid out in the setup, so the torque, the speed, it calculates the efficiency, and then starts to begin creating that efficiency map. It can even store the raw data. You can option out of storing the raw data if you want to make this file very short, but it also makes a separate XML file so that you can, and CSV file so you can store that table of results in addition to the efficiency map. And then it gets set, it gets itself set and ready for the next trigger. And you just go through that process very quickly. You could record for, say, for a half a second, and it'll be ready immediately after the trigger. So you can do every half second or every second perform a set point and an acquisition. And it's up to you how many you want to do. 100 set points, 200, 300, 1,000, however many you want to do. And then once it's complete, then you'll have a full efficiency map and a table that goes along with it with all the results, the torques, the speeds, the efficiency, and whatever you've decided, and you're done. So it's quite seamless, quite nice setup. Well, that about wraps up our webinar presentation for today. Everyone that registered and joined us today on the webinar will receive a emailed version of the presentation, and will receive a link as to when the webinar will be available on demand to watch again on our website. If you did send a question into our Q&A and we haven't gotten a chance to answer it yet, well, be sure to include your email so that we can answer your question over the next couple of days and get back to you. Thank you for your time and your patience. And we also would like to provide you with my email address here, mike.hoyer@hbkworld.com, if you have any further questions in the future, or you can call our technical support line at 1-800-578-4260, or email our technical support team at support@usa.hbm.com. Thank you very much for your time, and you have yourself a good day.